Okay? So this is just to fix notation. Okay, so now we are going to assume that that our weight, so I am going to assume in this particular case, so now I have contours, these are geometric objects, and I am going to assume that W gamma is more or equal than epsilon to the power gamma. Okay? This is my assumption. And usually, you know, we had two cases of situation like that. We had e to minus beta 2 beta gamma. It's clearly like that. Simply epsilon is e to minus 2 beta. Or we had this other case, high temperature case, that Alan was just referring to in his last lecture, and there was tangent hyperbolicus beta to some power. So for beta small, for high temperatures, we have again condition like that. Okay? So whenever we have something like that, we should verify that this is true. So first, again, you know, I somehow forget that Alan was denoting sides as i's. So here it is x just on
You're allowed to use your own notation.
Just on this slide, then I will switch to i's. Okay, so let us suppose that epsilon is so small that this is true, and x is the red point. So I have a set. I am summing over a set of all contours that contain a particular red point. Okay? And simply I take epsilon so small that this is true. You can imagine that this is easy to verify if epsilon is sufficiently small, because the number of contours is bounded exponentially, some, I don't know, 2d minus 1 to the power length of the contour or something like that. So it's easy to verify that this will be true. Okay?
So the summation is over what index?
So the summation is over gamma, over all contours that contain a given x. So I choose a point, I choose a red point, okay, and now I'm summing over all contours that contain this point somehow. Okay, sum over all of them with epsilon, and I somehow want slightly more, so I put e times epsilon to the power gamma.
So gamma here is your
Is my contour.
V over there. Or
Is my V over there.
Right.
Yeah? Okay.
And so over there, the V's didn't have elements, but now.
Yes, now it started to be really some object, some geometrical object. Okay? So having that, it's easy to verify that I have also this thing. Consider a contour gamma, and now I am summing over all contours that are incompatible with this gamma, that intersect it. Okay. What does it mean? They intersect it at some point x of gamma. So I can sum over x's in gamma, and then I sum over all gamma prime that contain a given x. Okay, I have e epsilon to the gamma prime, and this I assume is smaller than 1, so I have this inequality, it's more or equal than gamma, because the number of edges in my contour is certainly less than the number of these red vertices. Okay? Or it is otherwise around. It's certainly bigger than the number of red vertices. It would be exactly equal if it is just a loop, but otherwise it's bigger.
Is it possible the upper bound is changed to half the current energy gamma, because just do the pair gamma and gamma prime is one pair.
Yeah. I was,
I actually considered twice already.
Yeah, I was not, I was not careful at all here. So it can be.
It can be.
Yeah, it can be that it can be half of something like that. Yeah, I agree. Okay. So we have that, and now I want to check, and I choose, as I was hinting already last time, I choose R gamma equals 1 minus e to minus e epsilon to the power gamma. Okay. So this is my choice of R gamma, and I want to verify that the star is satisfied once this thing is satisfied. Okay? Okay, so I am going to start. So this is what I want to prove. I want to prove that epsilon to the power gamma is more or equal all this thing. Okay? Which is R gamma is this. Okay? And here is product of 1 minus I gamma. 1 minus R gamma. 1 minus R gamma is just this exponential, and the product is sum. Okay? So I have this sum here, And notice I have sum over gamma prime incompatible with gamma that differ from gamma. Okay, because this is in my graph, I took it like that. I didn't consider self-loops. Okay, but here in this bound, I can have everything, including gamma prime can be gamma, and still it will be true. Okay. Okay, so now I multiply and divide by e to the power plus e epsilon gamma, and I'm getting this. So I multiply by this. Okay, so I'm getting eta to this times -1. And here I have to divide, so I am adding, here there was sum over gamma prime incompatible with gamma, and here I added to this sum also the term gamma itself. Okay? And now, why he's not reacting, he is. And now I'm claiming that this is bigger or equal than e epsilon to the power gamma times e2 minus, there should be absolute value here. Okay? Why? Here this is simply, okay, he doesn't see me from such a distance. Here it is simply inequality e to x minus 1 is bigger or equal than x. Okay, so this is this thing. Okay, and here I use this thing. Come on. Okay, I use this thing having this bound, or this bound here. I plug it here and I am getting e2 minus gamma here. Okay, crossing this e, I have epsilon to gamma. This is exactly what I wanted to have. Okay, so this is just quick, just showing you how to check this, funny star inequality. Yes?
I just wanted to add that, I mean, there are some applications where the weight won't simply be a straight power like that. It might be a straight power multiplied by some other stuff.
Even that, and to my surprise, I found, because when we first wrote it, this other condition with David Price, but when we first wrote it, somehow we were thinking, okay, this is the best condition we know, but somehow it's funny to have this thing depending on your vertex or things like that. Okay, but then there was a paper by Leap and Kennedy, and they somehow were verifying something like that, but somehow they needed the weight to have different weight for short contours and long contours. Okay, for long contours they essentially used the standard upper bound, but for short contours they used computers somehow, because the bound is somehow, I mean, here you do not see it very well, but in our condition it was clear it is both on left hand side and right hand side, and you can optimize somehow.
Well, that's why.
And what they did, they optimized for somehow what weight to take for the short contours using computer in such a way, because they had a particular model and they wanted to show that cluster expansion can be applied.
Well, that's exactly why I was going to say that better, cleaner than this condition is the condition in the paper of David Price and somebody.
Yeah, okay, but it's slightly weaker.
Why is it important to find the largest possible neighborhood?
Because you have some models where you want to use it, and then you need it for this particular model. Imagine, we are just looking with Alan on a model where the weight is exactly 1/2 to the length of gamma. Okay, and then somehow your bounds, wouldn't be enough. So somehow, it's different lattice and whatever, but it's very close, and we had a difficult work to really see that it is sufficient what we have. We were just using Pire's argument, not cluster expansion, so we didn't need such a strong condition, but still. Okay, so sometimes you have a model, in particular this Leap Kennedy model was quantum model, but they translated quantum model into something classical, then they needed cluster expansion, and this was cluster expansion with a particle weights. And then, okay, you have to check whether this is satisfied or not with some RV. And now you choose your RVs in such a way that, and it's not enough to choose them as I'm choosing here as this thing. You have to choose them somehow different from short contours and long contours. It cannot be just, one formula. So what they did, they have chosen something like that for long contours, and for short contours, they used computer to find optimal values in such a way that this is still true. Okay, so we have, this guy is very insensitive. So we have this what we wanted. Okay. So, and now we start harvesting. Okay. So we have our cluster expansion and we can use it. So for example, in our low temperature expansion, in what I'm just describing here, we had the physical partition function was, up to some factor, was this partition, this partition function of our abstract contour model, where we took for v's, we took these gammas, and for their incompatibility, their intersection and things like that. So we had this formula, okay, where this LV here is the set of those contours that are somehow contained in lambda. So for example, there I should here, let me go slightly farther. Okay, let me go here. For every gamma, I can introduce V gamma, which will be the set of these red points crossed by my contour. Okay, and here I should say L lambda is the set of gamma such that V gamma is subset of lambda star. Then it would be correct. Okay, W gamma is actually there should be 2, E2 minus 2 beta gamma. Okay, and then we can simply show, we can, if beta is large enough, we can verify our star condition and we can start to use our conditions, okay? So in particular, we can show that this thing makes sense. We have a formula for it. And as I will show you right now, we can actually compute explicitly the limit, okay? So here is explicit formula for the limit lambda going to infinity of 1 over lambda logarithm z L lambda of W. Okay? And the formula is like that. You have sum over multi-indices of, any support. Vx containing a given point, for example, origin, the guy who is distance 1/2, 1/2, 1/2 from origin, one particle red vertex. And then you have your weight, Ax, Wx, but you divide by the number of points in Vx. Okay? So this is explicit formula for free energy, so to say. Okay? Which is really exact, rigorous, there is nothing, there is no approximation in it. Okay, so let me prove it for you quickly. So we look on that. What do we have? We have this formula over there. Okay? So this is the formula we have here. Now the other thing, there was 1 over lambda and I want to compute limits, so I multiplied it by lambda. So this is lambda times what I had here before. So I multiply by lambda the right-hand side. Actually, I repeated right-hand side somewhere here. Okay, so this is right-hand side. This is what I'm claiming will be free energy. So I multiply it by lambda. Okay. Now, lambda times this, I can as well write here sum over x's that contain a given size, sum over j's in lambda star actually, or something like that. And then I have sum over x's such that they contain exactly this j, because everything here is translation invariant. So whether I take for this 0, I take point at origin or point anywhere else, it is the same. So I can simply put here sum over I in lambda star times sum over x's such that Vx contains I and the same factor like here. Now I want to prove that this subtraction will contain a lot of zeros and there will be only small amount of terms essentially proportional to the boundary of my volume. Okay, so how we see that? Okay, so first of all, you can exchange the order of these two sums. So first I write sum over x's, and then how many i's I will have, all the i's that are inside of lambda star and in the same time inside of Vx. So I will have Vx intersection lambda star, okay, divided by this. In principle, I should write here sum over x's that, because I see that these Vx's contain I from lambda star, so this should be x's that intersect lambda star in some sense, okay? But since I have this number here, which is 0 if Vx doesn't intersect lambda star, so I can forget about any condition, and this is sum over all possible multi-indices. Okay, so I have this. And now you see immediately, I mean, if X is fully contained in lambda star, okay, then I have here Vx intersection lambda star is simply Vx, this disappears, and I have exactly the same term as here. So if Vx is fully contained in lambda star, I have exactly all those terms that are here are also here. So I will subtract them, and what will remain will be only a couple of terms that remain. These are terms such that they intersect inside, but also they intersect outside. They are not fully contained inside. So if you write those terms, so you are getting, I'm probably cheating here. There is nothing changed. So there should be only X that are reaching outside, and then the same factor as here. Okay? Yeah. Then I take absolute value of that, and I take upper bound of this, and what I'm getting, it is, if I have X that is somehow, sorry, now it's bad. Now I have to go back, and I have to go through all this very quickly, because I don't know how to do it. I do not know any way to do shortcuts without really switching off the screen somehow. As you see, I am totally inexperienced with these computers. Okay, I shouldn't overdo it. Now we take absolute value, and now we bound it by something. So we have my volume lambda here, and I am talking about clusters, and now I use the fact that it is a cluster. Okay, so I have cluster like that, and I know that it has to have something inside, but it has to have also something outside. So it has to cross the boundary. Okay, so I can pin the point where it crossed the boundary. I can sum over points at the boundary, and then sum over all clusters that contain this given point. Okay, and this sum is exactly something that I have here. I can actually bound it by sum like that. Okay, so I am getting a constant for this sum. I am getting a constant times length of the boundary. Okay, but this was somehow the term where I multiplied, everything was multiplied by lambda. So now I divide by lambda, and I see that the difference of two terms, the difference of the term that goes to the limit and the term that I am claiming is a limit, differs by length of the boundary of lambda divided by lambda, which goes to 0, of course. Okay, so now I can go to the next page. So I can really claim that this is my limit. Okay? Okay, so and then we have immediately a couple of immediate claims. For example, we know that this partition function was, we wrote our low temperature partition function in that way. So we are able to claim immediately that F beta 0, free energy at temperature beta with 0 external field, because this is what we had, is analytic in beta for beta large. Okay? Because it is absolutely convergent sum of terms like that, here we have this explicit formula of terms like that, okay? And how they depend on beta, I mean, there is this W to some power, so there is some polynomial in E2 minus 2 beta. Okay, so it's perfectly analytic function in beta, and now I have absolutely convergent series of those. Okay. So I see, for example, immediately that F beta 0 is analytic for high temperatures, and similarly you can use the high temperature expansion, this tangens hyperbolicus type of expansion. You can show there our factors W gamma. There our weights contained, there was tangents hyperbolicus to beta to some power, and tangents hyperbolicus beta h to some power So again, we have perfectly analytic functions in beta and h this time, okay? And we have absolutely convergent series of those terms. So we have free energy this time that is, F beta h is analytic in both beta and h at high temperatures. Okay? And let me just mention another application that is somehow that is very important for us. It was very important for applications in statistical physics, somehow in mathematical statistical physics, but it's still a lot of work what you have to do. But somehow I just want to indicate what you can do. So somehow if you look, what is the typical configuration if you have this plus boundary condition here, and now you look on typical configuration. So given the fact that contours are improbable, as we have proven here, you have only small contours here and there. And actually you can compute with what probability what contour will occur. For example, the smallest contours like that, their weight is e to minus 8 beta, so they should occur somehow with density e to minus 8 beta. And then the next ones, those with the length 6, so it is e to minus 12 beta, so they will occur with density e to minus 12 beta. So somehow looking on a configuration, you can decide, is this a good configuration or not? Is this configuration corresponding to the equilibrium state at a given temperature beta? Okay. Now imagine that I somehow enforce the condition that I want this, but in the same time, I need that sum of sigma i's is a fixed number, is some fixed fraction of the volume. For example, 1/3 of the volume. Okay, or maybe something smaller, maybe 1/10. Okay, so it is so I'm enforcing that. Of course, I could somehow try to do the following thing. I could try to put somehow more bigger contours here and there to achieve this number. Okay, but this would be very costly. This would be very expensive. And the cheapest thing you can do is that somehow you have a big region that will be essentially minus region. So you have pluses here with some small islands here and there, and then you have a lot of minuses here with some islands of pluses here and there. Okay? And now you can study what is the probability distribution of the shape of this bubble. Okay? This bubble is called in physics, Wolf shape. So there is some variational principles that somehow say you something about the shape of this bubble. On the square lattice, it will not be rounded like that, but it will somehow remember the shape of your lattice. It will be somehow square-like potato. And now if you want seriously study this, so you draw this line here microscopically. I have this line here, okay? And now I have partition function minus partition function inside and plus partition function outside. And what I can do is that, okay? But having cluster expansion, I have explicit formula for partition function in any volume. I can use this formula, and it will give me, so I can forget about this gas of contours outside and inside, and replace it by some clusters here and there. Okay, but there is a universal value of this cluster, which is the free energy. So if I divide by free energy times the volume, what will remain here? I'm really somehow doing it very quickly, but what will remain will be clusters that are intersecting my boundary here. So what I'm getting is the boundary decorated with these clusters. And now the task is somehow to study the probability distribution of boundaries decorated by these clusters, and 200 pages on, you are able to prove that the typical shape is really something like that. Okay? Okay. So this was one somehow really advanced application of cluster expansions. But let me now mention one important thing. In all that, we were talking about Ising model, only Ising model. And there the symmetry between pluses and minuses was very important. So I would like to devote second half of my talk to the case where I have no symmetry, where the symmetry is lost. Then I have to do something. I was somehow hoping that, within 1 hour and a half, I would be able to jam this, one semester talk into hour and a half, but I will not be able to do it in half an hour. But I will try to somehow to give you some flavor of this. Okay, so this is so-called Pirogov-Sinai theory, and this is a theory where we do not have this plus and minus symmetry. Okay? So what is the simplest example we can look at this? Imagine we take simply our Ising model, this, and we add a term that is somehow breaking the symmetry between pluses and minuses. So here I choose the simplest possible, I choose some small kappa times some over all possible triangles, this is I, j, k, these two are nearest neighbors and these two are nearest neighbors, so these are triangles like that. I have sigma I, sigma j, sigma k. So I have this triple interaction, okay? And of course, if I have 3 pluses, it gives me plus. If I have 3 minuses, it gives me minus. So it's somehow, it is breaking my symmetry. For example, if I have exactly the same contour, if it is, contour where I have pluses outside and minuses inside, there is some weight. But if it's otherwise, if there are minuses outside and pluses inside, the weight is different. Okay. Still, I can write my partition function in the volume lambda. I can write a sum over collection of contours. There are the weight of the contours, but now the weight of the contours contain also a piece coming from this gamma. So they already lost the symmetry as I am showing here. They might have different, so they remember somehow what is outside of the contour, what is the color of the contour, what is the sign of the contour. So this is one thing. And then in the regions in between, maybe let me show you the picture. Okay, so this is my configuration. I have my contours. Okay, I have region covered with pluses. I have regions covered with minuses. Okay, and and I do not know. So even the energy of this, of these regions will play a role. So there will be a term that will give me minus beta E plus, which is the energy of the pure plus region, times the area covered by this plus region. That depends on my configuration of contours. Minus beta energy of minus regions, somehow, times the volume of minus regions. Okay? In Ising model, if you had Ising model at non-zero h, you would also have something like that, because you would have different plus and minus regions. But in Ising model, we knew that we are looking for transition at h equals 0. So we put from the very beginning h equals 0. Here we do not know where the transition, for which h transition occurs. Okay? So we should somehow deal with these more complicated partition functions. And in addition, so here I show you, that the weight of such a contour and such a contour can be different here. Okay? And in addition, we do not know where the transition happens. Okay, so there is, in Ising model, the transition line was simply h equals 0. Here we have some unknown transition line ht beta. There are, for every beta, there is a point, for every beta large enough for low temperatures, there is a point where we have transition between, mainly plus regions and mainly plus phase and mainly minus phase. But this transition happens at some value of h, which we do not know beforehand. So the theory has to deal somehow with this, with the more complicated partition function, and also with the fact that in the same time we have to compute the phase diagram. We have to find where it happens. Okay? And the thing we are losing here from say Parse argument, we cannot use Parse argument because if you erase a contour, you take it away, you have a new configuration. The new configuration will have, red will extend over the region where this was green before, and this inside it will turn into green. So not only you will change the regions of here, this would be not so serious, but you change the weight of these contours. Because now they are contours outside, they have the same geometrical shape, but outside they have pluses, and before they had outside minuses, and they have different weights. Okay? So this is a serious problem. Okay, so there is this fact that for us, the independence of contours was very useful, because then we were talking about independent sets, and independent sets were somehow pairwise independent. It was not somehow global thing, but it was pairwise independent set. Here there is something like long-range interaction between this contour and this contour, because if we take this contour away, this contour will feel. Yes, so they somehow know that there was this big contour around them, and if you take it away, the small contours inside, they will start to shiver because something happened. Okay? Okay, so we can recover this independence by a crazy trick invented by Pirogov and Sinai. Even so, I mean, here I am presenting it in somehow different way. Okay, I will comment maybe later. Okay, so what we can do? Imagine I will first look on the most external contours. So theta is the collection of most external contours. And I will resum about everything which is inside. So I have, I have somehow weights. I have my most external contours. I have their weights. I have product over gamma in this set of most external contours. I have some weights. And then inside of the most external contour, so for example, here I have such a external contour. So immediately, if this was plus, if outside I had pluses, so then immediately here I have minuses. Okay? So I can look on this as resumming over everything what's happening inside is just partition function with minus boundary condition on some interior. Okay? So now nobody can prevent me by dividing and multiplying by z plus. Okay? And then I will take all these guys and call them new weight function W plus, and I will have, so I will have plus contours that inside has again plus. Okay? Okay, so I introduce this W plus. Okay? And having this W plus now going by induction, more and more inside, I can simply rewrite all my partition function as sum over collection. Now these are again standard collection of plus contours. All of them are plus contours, which is geometrically impossible, but I forget about geometry now. I have simply plus contour, and inside that I have another plus contour, and inside that I have another plus contour. Okay, totally artificially. So I have this, and I have just standard contour, or how I call it, abstract polymer representation here. Okay, so I can use again my standard technology, because here the contours, whether they are present or not, nobody notices because they somehow do not change any color. All of them are plus contours.
The thetas were contours with an additional no nesting constraint.
Pardon?
The thetas were contours.
Well, I slightly cheated here. I mean, this is not exactly the partition function in the volume, because here I am not allowing these thetas to touch the boundary of lambda, because I want to keep my hierarchical induction going. So somehow I should think about this volume as an inner boundary of some contour. So there shouldn't be contours that are touching it, because they will glue with the contour outside.
Yeah, but
Yeah?
all I meant was a more general point. The thetas there's a no nesting constraint. You can't put inside
They are
of it.
external, yeah.
But then you resummed it to get back to completely ordinary contours.
Yeah.
Is there a missing Z+?
Z plus and gamma is missing.
No, because one by one there was Z plus of gamma, but Z plus of gamma from the preceding, somehow from I do it by induction, and preceding I had already this formula, so I simply replaced Z plus of gamma, this Z plus of gamma here, I replaced it by interior contours but plus contours. I used by induction simply this formula. So the claim is I want to prove this formula, and I prove it by induction. So I start with such small contour plus that I cannot have any other contour inside. Okay, for them it's true. Okay, now I start with contours that have already something inside, but this something is already smaller, so I can use already this formula and so on, and I can somehow telescope this until I have the full formula.
These contours have a tree-like structure.
Yeah,
The way
they are.
nest.
Yeah. Okay. Okay. So this is my contour representation here. The abstract polymer representation. Okay. So I recovered independence, but I lost something. What I lost? I do not know whether this W plus gamma, whether they have sufficient decay. Before I had, W gamma was E2 minus 2 beta gamma, but now I replaced it by something like that. Maybe this has some volume term in it, and I lost this W gamma. Okay, I lost this E2 minus beta gamma. So I might have lost sufficient decay condition. Okay, so what I will do now, I do very crude thing. I simply look on this W plus. Okay. And if they are decaying sufficiently, I mean, here maybe I should write epsilon to the gamma with epsilon satisfying the star condition. Okay? So if they satisfy that, I keep them. I do not touch them. If they do not satisfy it, I simply replace it by epsilon to gamma. Or there is other version of this, I replace them by 0, the weight by 0. Okay? I simply forbid those contours that would have too big weight. Okay? So this is W plus bar. Having this W plus bar, I can of course consider partition function. I call it Z plus bar, which is this, which is like physical partition function where, however, I replaced this contour part by this W plus weights. Okay. So it is if I were putting 0 here, this is like partition function where I suppressed all contours that would cause any problems. Okay. And this satisfies perfectly, or this satisfies cluster expansion, so I can write, limit of logarithm Z plus of this, and I can compute free energy. Free energy will be, free energy is minus 1 over beta, and now limit lambda going to infinity, logarithm of 1 over lambda, logarithm of Z lambda. So there will be this E plus term coming from this first term, and then there will be this limit, but as I have shown you before, I can even write explicit formula for limits like that. Okay? So I have free energy, F plus. And similar thing I can do for minuses. Okay? I can introduce W minus. I can, in the same way I introduce W plus here, I can introduce W minus. I can introduce W minus bar. I can introduce Z minus bar, and I can introduce F minus. And nobody is saying that F plus and F minus are the same functions. They will be different. Okay? So now the question is this, useful, whatever, for something? I did, one artificial step, second artificial step, then I have some funny free energies. Okay?
In free energy formula here, remind me what E plus is.
E plus is the energy of situation where I have C of pluses. So it's energy per side of pure pluses. Yeah? Okay. And now the magic happens. And the magic is that if you take these two functions, F plus and F minus, that we perfectly constructed, their minimum happens to be exactly the free energy. Okay? So in picture, it looks like that I have, I have the function F plus. I have the function F minus. The real free energy is their minimum. It's a function like that has a corner here. And where it has corner? Exactly at the point where transition is. So I can find transition by simply writing equation F plus equals F minus, and this will be my transition point. For large, this picture is for fixed beta, sufficiently large beta.
This is true no matter what this artificial cutoff taught you?
Yes, and now I need to explain you why it's true somehow, but
The cutoff of tau equals 1,000,000?
it's,
It grossly perverts these weights?
well, the cutoff must be such that the remaining thing satisfies cluster expansion somehow. Yeah, so it is 0, for example, or E2 minus tau gamma or something.
No, but I mean, I make a hugely strong cutoff.
No, but the cutoff is determined by the contour himself. You look on its weight. I will try to explain, okay? So let me forget about this is the claim that F is this. Up to now I have only this F plus and F minus, and I introduce I take the minimum of them, forget that it is F, I take a minimum of F plus and F minus, okay? And for example here, this is A minus. So A minus is the difference between F minus and F plus if F plus is the minimal one. So here this is A minus, here this is A plus. So essentially this A plus and A minus measure distance from my transition point, from unknown transition point, okay? And somehow contours know about, what is transition point. They know if you start, I have, recall the formulas. W plus was W gamma times, the ratio of these two partition functions. If I am very close to the transition point, then these two partition functions, their ratio is essentially 1. And I have nice contour, and I needn't make any changes, okay? So there is the following lemma, okay? So I consider this kappa, this was my asymmetry factor, this triangular interaction, and H such that some condition is satisfied, okay? Kappa is simply small enough. And suppose that A plus is 0. A plus and A minus are defined in such a way that always either A plus or A minus is 0, because it's F plus minus minus minimum of those, okay? So always one of them is 0. So let it be A plus. So we are here, and A plus is 0. A minus is this, A plus is 0, okay? Then for sufficiently large beta, and now the proof of this lemma goes by induction, so there is this for every n, but the n is only for purposes of induction. You can forget about it for the final statement, so to say. If you have a region whose diameter is smaller than n, so this is the thing you can forget, but A minus times diameter of lambda is smaller than 1, so diameter of lambda is smaller than 1 over A minus, then W minus was already was satisfying the condition, and W minus bar is the same as W minus. Okay, so no change was needed. So what it says that if you are in a volume that is somehow, if you are very close to the transition, which means A minus is very small, then 1 over A minus is very huge, and in the volume up to 1 over A minus, no need of redefinition is needed. Your W minus is good. So somehow the model, if you think about what happens with the model, so if you try to enforce boundary condition, so let me first finish and then somehow, and then there is a second statement, and this is that this is true for W plus, it's always true. Okay. Always if diameter is smaller than n, but you are proving this by induction in n, so at the end you have this. Okay? So simply here, if I take a point here, then for W minus I needn't do anything all the time, and for W plus, and for W minus I needn't do some redefinition only for very large contours. So essentially it is saying that close to the transition, both phases believe they are stable. Okay? If you try to enforce plus boundary condition, it will stay. You will see sea of pluses with some small islands. And this happens for every contour. Whenever you try to enforce pluses, it will stay like that. Whenever you try to enforce minuses, then for small volumes, since you are very close to the transition, it is not somehow, we know that the real stable phase here in this region is plus phase. So eventually it will flip to a plus phase. But for small volumes, there is somehow the cost for flipping over this somehow over long contour around the boundary from minuses to pluses is so huge, and the gain in the energy inside is so small that you better do not flip. And you simply, and your contour your minus somehow boundary condition propagates inside, and it's somehow you have sea of minuses and only small island of pluses. Only if the contour is very big, but very big in comparison with what? In comparison with 1 over A minus. And A minus depends on where you are, so everything is fluid here somehow. Okay? But this lemma can be proven. Okay?
And this is true no matter how big I take tau? I mean, I could take tau to be...
No, you should take tau such that tau is coming from star. So tau is my epsilon.
No, but if I make tau bigger,
even better.
It becomes more true because I'm cutting it more.
Yeah, but you are bigger tau means you are at lower temperature.
Go back.
Do not ask me to go back because
back.
this is you really want it.
I thought the point was that tau is an arbitrary cutoff, right? I thought
no, tau was, okay, tau was, chosen. Let tau for me is a fixed tau that is chosen in such a way that my cluster expansions work.
Yeah, but I thought the point was I'm taking the actual weights W plus and replacing them by weights W plus bar that are cut off with e to the minus tau gamma. So if I take tau big, I'm cutting it off at a function which is smaller, then it all the more the cutoff ones satisfy the cluster expansion. So I'm cutting it. So I guess the only reason that it could hold for large tau is that, I mean, if tau is huge, then maybe I'm making A minus huge.
No, you have to use, that your W plus of gamma is W gamma, which is somehow small by definition because it's E2 minus 2 beta gamma, and then it is Z minus over Z plus. Okay? And here we are talking about, what is the ratio of these two guys. This guy is small enough.
But whatever, I don't understand, whatever W plus is, W plus bar is W plus with this cutoff e to the minus tau gamma, right? So can't I always make it satisfy the hypothesis star?
No, because you need somehow, it's hidden here in this condition, is hidden that you have W gamma, which is small enough. Okay, I am saying this should be smaller than 1, which means that these corrections coming from kappa will not destroy too much W gamma, and W gamma will be still small.
But
the raw somehow W gamma, and then I say for sufficiently large beta. So somehow in the proof it occurs, W gamma plays a role.
But sufficiently large is tau dependent? Is that the problem?
Tau for me is fixed number, like logarithm 5.
But what if I take tau to be 1,000,000?
Then you have to take probably beta bigger.
So the point is sufficiently large beta is beta of tau.
Yeah, exactly. Okay, so let me, I started 5 minutes later, so I have still. If you have several phases, I was showing you the picture where I have only 2 phases. But if I have several phases, everything works like exactly the same. I only have to introduce several models Wm instead of W plus W minus, okay? So several phases, I don't know whether it tells you something, but essentially several colors. If I have, imagine I'm talking about something like Potts model at low temperature, so I have Q different colors, and I introduce some external fields, for example, okay? And now I want to study phase diagram of this model, okay? And I can define these functions Fm, okay? So I have Q of different Fm functions, and now I can look which one is winning where. I was saying my transition point was determined by saying that F plus equals F minus. Notice that this Fm, they are somehow, they are defined, this is really, the definition is somehow recursive and everything, but they are defined. There is somehow well-defined construction. They are simply defined, okay? So I have these functions Fms, depending on some external fields, and now I look on phase diagram, which will be given by coexistence of these Fms. I will simply draw the picture like that, where I somehow look on the region in so I have some external fields, okay? and I have regions where F3 is the minimum, I have region where F1 is the minimum, and I have the region where F2 is the minimum, and then I have lines where F3 and F2 are giving me exactly the same value, and I have line where F1 and F3 coincides, and I have line where F1 and F2 coincides, and I have a point where F1, F2, and F3 coincides. So I always have a phase diagram like that. Okay, so if you somehow fully state this Pirogov-Sinai theory, it is saying something about the general phase diagram of a situation like that. Okay. Okay, so this is, so this is the main thing of Pirogov-Sinai theory, is to construct phase diagram. But there are other somehow applications, and let me just mention two of them. And one of them, and both of them are somehow based on one crucial corollary. And the corollary is the following thing, that if I take periodic boundary conditions, so now I consider partition function with periodic boundary conditions. So let me recall you, I am talking about, say, about the situation where I have two phases, so I have this F plus and F minus, okay? And I have, so the claim is that partition function with periodic boundary condition is very well approximated by just the sum of two terms. One is E2 minus beta, my plus free energy, times volume, and the other is E2 minus beta, my minus free energy times the volume. Okay? And when I say are well approximated, I mean you can really prove that the difference of this can be is bounded, somehow by again the same the term like that, E2 minus beta real free energy, okay, times the volume times something exponentially small, E2 minus diameter of the volume, or E2 minus beta diameter of the volume, or something like that. Okay, so it's really somehow behaving very well, and not only that, but also if you take the difference and compute derivatives of this, so also you can bound derivatives quite well. So what we needed, about 3 derivatives or something like that, we can bound. Okay, and then when you have this, you can use it to compute different things. So one thing is you can study finite size fx, okay, because you simply replace your partition function by this, okay, and then you compute, say, what was magnetization. Magnetization was derivative of logarithm of free energy with respect to h. So I take logarithm of this sum of these two functions, compute derivative with respect to h, and explicitly see that I'm getting something like tangens hyperbolicus in h, okay? And of course, all the errors can be exactly computed, so then you can claim that your magnetization is within some distance from an ideal curve that is tangens hyperbolicus, that the drop is over the region 1 over volume and things like that. So all this can be proven, and also, for example, you would like to define where is, if you interpret your Monte Carlo simulations, you have a curve like that in finite volume, and you would like to see what is the distance of the transition point from the real transition, from infinite transition point, okay? So using this theory, you can really somehow find asymptotic descriptions. Imagine that my transition point is a point where the slope is maximal here. Okay, so I choose this point. This will be ht on dependence of my volume. This is infinite volume, so ht of L. And I can ask what is asymptotics of ht of L minus ht, and there are formulas for that. Okay, so this is one application. But somehow it turns out that the same formula as here can be extended even to complex values of external field. Okay, because these constructions, you are doing this, this construction of f plus and f minus. Somehow, if you think about it, there is nothing that really prevents you to take for h to take a complex values. Okay, so then you can study zeros. Okay, so you can study zeros of partition function with periodic boundary conditions, say. Okay, and what turns out that zeros you can prove simply that the zeros are somehow asymptotically lying on curves, now your free energies, so imagine I'm drawing here the situation. I should have generalized this for several phases. If you have more phases, then your Z with periodic boundary condition equals sum over m E2 minus beta Fm times the volume. So equals, it doesn't differ too much from this, okay? And now you can somehow, but now Fm's can be complex functions because H is complex, so so Fm's are complex functions. But it's clear that somehow zeros here can occur only when you have just finite sum of couple of terms. So when these terms have the same absolute value, so the real part of Fm is the same, and then the imaginary part somehow, as you move along this line where real parts are the same, then imaginary part is giving you zeros. Okay? Then the somehow fluctuations of the imaginary part are giving you zeros, and you can compute the density of zeros and things like that. But what you see somehow that zeros are essentially milestones between regions of different phases of the phase diagram in complex domains, so to say. Okay? And what we can really prove is that somehow, okay, so you have these lines where real part of F1 equals real part of F3, for example, here. And then you have some fake zeros where imaginary part of F1 differs from imaginary part of F3 by 2k pi, okay? So this will give you zeros on the line. And the real zeros, I mean, because there are these errors, we are not really saying that it equals. So the zeros of real partition function of the, I shouldn't say real because it's complex, so how do you say the true partition function, yes? The zeros of true partition function will be not exactly on this line, but slightly away, but they will be at distance E2 minus beta L from this line. So there will be, for low temperatures, they will be very close to this line, okay?
With 3 or more phases, they would be off the line anyway, right? Because on the 1-2 coexistence, there's a little perturbation from term 3 in the sum.
Yeah, but it's, this formula is really true, so you can see what this third term is doing. So of course, near this bifurcation point, it's somehow getting worse. So the error bounds here are somehow worse, but outside, if you are somehow outside of the region, I don't know, 1 over volume or 1 over square root of volume away from this point, then it's already nicely exponentially close, okay? And you can use this reasoning to reprove, so this will be last thing I will say, to reprove the Lee-Yang theorem without using any multivariate stuff.
But only at very low temperature.
But only at very low temperature. And the proof is somehow amusing because what you do is, there is this symmetry. So F plus and F minus, there is symmetry between them, okay? So in particular, it means that this coexistence line is exactly a circle. So this is, the line where real part of F plus equals real part of F minus, okay? So now our claim is, first of all, we know that the real zeros are at distance exponentially close to this circle, and their mutual distance is 1 over volume. Yes, because somehow we can prove that the density is governed by, derivative of difference of imaginary parts or something like that. So you can prove also that their distance is 1 over volume, okay? Now, if I have 0 here, then by simply using this symmetry, I can construct another 0 somehow taking, I don't know, 1 over z transformation sends me here, and then somehow complex conjugate, or so I do 2 transformations, and I will create new 0 which will be inside of my circle. Okay, again very close to the circle itself. The distance here is E2 minus beta L. The distance here is E2 minus beta L. But I know that 2 different zeros have distance 1 over volume. So this cannot happen, and it means that I should have started from 0 exactly at the circle.
For sufficiently large L.
For sufficiently large L and sufficiently large beta.
So it's amusing. You prove the Lee-Yang theorem only for big graphs.
Yeah,
which
Yeah.
one would think is the hardest.
yeah, yeah,
You can't prove
Well,
the
all
Lee
this
Yang
is, you
theorem
know,
for small graph.
yeah, yeah,
Prove it asymptotically.
yeah.
Right.
And it's, you know, what is funny, you know, there is a model that is called Bloom-Couple model, where there is another phase called zero, and this zero phase makes some sort of, you know, some intrusion here. So there is something like that. Here you have a real part f minus, real part of f plus, and here you have real part of f0. This is the third phase. And here, these curves are somehow, you can approximately compute them, but these are non-circular curves, some curves, okay? There are these bifurcations for here. But this line is again exactly the circle, and the zeros by the same argument must lie on this circle exactly. Okay, so even if you have a model that is only have this partial plus minus symmetry, only somehow there is another phase, but still there is plus minus symmetry, you have this. By the way, for Potts model it looks exactly the same. If you, this is, you know, if you have Potts model with some, with external field favoring one phase, so, and you are close to the transition temperature to the disordered phase, so this is disordered here. You have, you know, you have ordered phase, you have some other phases here, the remaining somehow, and then you have the disordered phase here. But it looks like that, and then it is not circular at all. I mean, we can prove that it's, we can compute sufficiently enough terms in the expansions showing that it's not close to circle.
Or do you need the ferromagnetic conditions?
No, we do not need any ferromagnetic, no.
You don't need.
No. We need applicability of Pirogovsky theory. So there is some, you know, something about contours, the weight of contours, and things like that.
So you would prove the Lee-Yang theorem for large volumes and low temperatures for some easing model that's not completely ferromagnetic, as long
Yeah.
as it's predominantly ferromagnetic.
Yeah, yeah, sure. Sure, because you have this simply, you have these phases, and you should be able to prove that the boundary between, you pay a lot for the boundary between phases, but what the phases are, they might not even be translation invariant. Phases might be some, like antiferromagnet or something. You know. Okay, so now I really went over.